Let's look at an example. If you're asked to graph any of these, this is sort of a 5-step process that I would follow every time. So first step is to get the end behavior. So look back at page 1 of the guided notes at those 4 cases we had for end behavior and take a look at this particular function and identify the leading coefficient and the degree. So hopefully you see that the degree is 4, which is even, and the leading coefficient is 1, which of course is positive. So go back and look at your notes. What did an even degree polynomial do if it had a positive leading coefficient? And you should have said it rises on the left and rises on the right. Step 2 would be to find the zeros or the x-intercepts. So to do that, we're always going to set the equation equal to 0. In other words, we're replacing the y with a 0. And then you're going to factor it. You won't have any that don't factor. These are all going to work out pretty nicely for you. So we've got x to the 4th minus 2x squared plus 1. It's a trinomial. There's no GCF. So the only thing we could do is go right to the 2 binomials that would multiply or FOIL out to get you this trinomial. If the first term is x to the 4th, that means we must have x squared and x squared as our first terms. They've got to multiply to 1. We're looking for numbers that multiply to positive 1 but add to negative 2. Multiply to a positive means the signs have to be the same. Add to a negative, that means they both have to be negative. And 1, of course, is just 1 and 1, so it's got to be 1 and 1. Hopefully you see that you have 2 difference of squares here, so this breaks down into x plus 1 times x minus 1, and then the same thing, x plus 1 times x minus 1. Now to help us out with the multiplicity, I would put these together according to common factors. So in other words, I've got x plus 1 times x plus 1. I've got 2x plus 1 factors, so I'm going to write that as x plus 1 squared. And then I've got 2x minus 1 factors, so I'm going to write that as x minus 1 squared. Now to actually get the zeros, we have to use the zero product property to set each of those equal to 0. So let me come over here and do that. We've got x plus 1 squared equals 0. We've got x minus 1 squared equals 0. Square root both sides here. We get x plus 1 equals 0 or x equals negative 1. What's the multiplicity for that? And that's 2 because of the squared factor. How about over here? Do the same thing. Square root both sides. We get x minus 1 equals 0. So x equals 1 is the x-intercept. And again, it has a multiplicity of 2. Notice the multiplicities add up to the original degree. Step 3 is to find the y-intercept. So how do we get y-intercepts of a function? Well, to get x-intercepts, we replaced y with a 0. So to get the y-intercept, we're going to replace x with a 0, just like we did in chapter 2 when we graph lines. So I'm going to go ahead and replace the x's with a 0. I'm going to rewrite, instead of f of x, I'm going to write it as a y. So we have y equals 0 to the 4th minus 2 times 0 squared plus 1. Make sure you see where I'm getting this from. This is the original polynomial. I've just replaced the x's with zeros. And so that simplifies to 0 minus 0, of course, is 0 plus 1. So we get a y-intercept of 1. Step 4 is to determine the symmetry, whether or not this is an even or odd function or neither. Remember, it could be neither. In chapter 2, we had a 3-step process for figuring out whether it was an even or odd function. I'm going to let you use a shortcut for this. When we're looking at polynomials and you want to decide if it's an even or an odd function, it's really pretty easy to do. You can just look at the exponents across the polynomial. And so if all of the exponents are even, then it's going to be an even function or an even polynomial. If all of the exponents are odd, then it's going to be an odd function or an odd polynomial. And if the exponents are mixed, even and odd, then it's neither. So let's look at this example. We have exponents of 4, 2, and 0. Remember 1, that's like x to the 0 power. A constant would just be x to the 0. I'd consider 0 to be an even number. So we've got 4, 2, and 0 as the exponents in this polynomial. So if those are all even, that means that it's an even function. And remember what kind of symmetry even functions had? Y-axis symmetry. Remember, odd functions had origin symmetry. Even functions have y-axis symmetry. Last step before we graph is to find the max number of turning points. So remember, that's n minus 1. In this case, n was 4, so we're going to have 3 turning points. So let's go ahead and put all this on the graph and see what happens. So we had intercepts, we had x-intercepts at -1 and +1, and we had a y-intercept in step 3 of +1. So I'm going to put those points on the graph. Then you're going to take your leftmost and your rightmost x-intercepts, and you're going to draw the end behavior. That's the next thing I would do. We said both ends go up, so I'm going to make the graph go up on those 2 points. Now here's where the multiplicity really comes into play. We had an even multiplicity for x equals -1. The multiplicity was even. So what did we say when the graph has even multiplicity at that x-intercept? We said it was going to touch the graph, it was going to bounce, touch it, and turn back around. So what that means is, since this is even multiplicity, the graph's coming down. It's decreasing, decreasing. It gets to that x-intercept. Instead of crossing through the axis, it's going to bounce and turn back around. And it's got to somehow give it up to that y-intercept, so it's going to have a turning point up there, and then it's got to get back down to this +1. And by the way, what was the multiplicity at the x equals 1 value? It was also even, so it's going to bounce again. So it's going to come down, bounce off that x-intercept, and turn back around. So there's our graph, and notice it has what kind of symmetry? Y-axis symmetry, and that's what we expected. Okay, last example. Let's put all this together and do another graph. So step 1. At this point, I would go ahead and turn the video off and try the steps on your own, and then watch the video after each step to make sure you've got it correct. So step 1 was to find the end behavior. So in this case, we have a degree of 3, which is odd. We have a leading coefficient of 1, which is positive. So look back at your notes. When we had an odd degree and a positive coefficient, what was the end behavior? We said down on the left, falls on the left, rises on the right. Step 2 is to get the x-intercept. So I'm going to set the equation equal to 0, and I'm going to factor it to solve. We only have 2 terms here, but we do have a GCF of x squared. So I'm going to take out the x squared, and that leaves me with x minus 3 in parentheses. And then we're going to set each of those equal to 0. So I've got x squared equal to 0 and x minus 3 equal to 0. X squared, take the square root, we get a x equals 0. And what's the multiplicity of that? It would be 2 because of the squared term that it came from. X minus 3 equals 0, so we get x equals 3. That was only raised to the first power. Back here it was just to the first power, so the multiplicity for that is 1. And notice what the multiplicities add up to. 2 plus 1, of course, is 3, and that was our degree. So that's a little check that you did that right. Step 3 is to get the y-intercept. So to get the y-intercepts, we remember we place x with a 0. So I'm going to go back to the original polynomial, and wherever there's an x, I'm going to substitute 0. 0 to the third, of course, is 0. 0 squared, of course, is 0. Times 3 is still 0, so I get a y-intercept of 0. By the way, if you get an x-intercept of 0, you should get a y-intercept of 0, because that means it's going through the origin. So that fits with what we would expect here. Step 4 was to determine if it has any symmetry. In other words, determine if it's even or odd or neither. So remember to do this, use the shortcut. Look at the powers. So if the powers are all even, then it's even. If the powers are all odd, then it's odd. If the powers are mixed, then it's neither. So what are my powers here? I've got a 3 and a 2. So that's one that's odd, one that's even, which is mixed. So that means it's neither even nor odd. In other words, it has no symmetry. So when we graph it, there's no symmetry to look for. Step 5 was to determine the max number of turning points. So remember, turning points is n minus 1. So in this case, that's 3 minus 1, or 2 turning points. Let's go ahead and put this all together. So my x-intercepts were at 0 and at 1. My y-intercept was at 0, so I've already got that point on the graph. Let's take care of the end behavior. So we said it's going to go down on the left, and it's going to rise on the right. Now, the multiplicity. So at x equals 0, the multiplicity was even. So that means it should bounce or touch the x-axis and turn around. So it's going to be increasing, increasing. It's going to get to that point. Instead of crossing through, it's going to bounce and turn around. Now, how far down it's going to go, the only way to really tell would be to plot a point between 0 and 1 and get an extra point on the graph. We're not going to worry about how far down it goes. Don't exaggerate it, but just go down a little bit. It's got to have a turning point down here somewhere because it has to get back up to this x-intercept. So I'm going to come down a little ways. I'm going to have a turning point, and I'm going to turn back around. Now, what was the multiplicity at the other x-intercept, remember, it was odd multiplicity, which means the graph should cross through the x-axis there, and that's what's happening. So we've got 2 turning points, which is what we expected, and it has no symmetry. So I think we're good to go on our graph.